Okay, let's go ahead and finish up these last four on page 7. So I marked letter C as a test question, but I also went down here and said this is a good one too. Letter C is a little more like the test because it has radicals in both, but both really good to practice on. So we see that on C, they're already divided up, and you can see why. There's nothing common. So we can start out with cube root 4. And then in the denominator, remember, we want to break it down because we need to decide what's missing. And there weren't any perfect cubes up here. That's why I didn't break it down. 2 2s, not enough to get out of jail. But this one we do want to break down because we need to realize what's missing. And I will tell you, this is a step most students miss on the test. They go, oh, we have 1 9. We need 2 more 9s. Well, you're supposed to break it down before you do that. Then you make the numbers much smaller than 3 9s, which is 729, or 3 3s, which is 27. Much easier to break down. So we know we need to get rid of the radical in the denominator, so that's why I wrote it as 2 3s, 2 x's. Now I say to myself, wow, this is a denominator or a index of 3. Because the index is 3, that means I need 3 of everything. So I have to decide, what am I missing? Well, I have 2 3s. I need 1 more. And I have 2 x's. Excuse me, I've been making too many videos, 5 classes, that's a lot of videos. 2 x's, and I need 3, so 1 more. Whatever I do to the denominator, though, remember I have to do the same thing to the numerator. So that leaves me with cube root 3x over cube root 3x. So this is really just 1. Multiplying by something over itself is multiplying by 1. But what it's going to do is get rid of the radical in the denominator, which is my goal. So in the numerator, we now have cube root of 12x. They're both under the radical, so we can multiply them together. In the denominator, we now have 3 3s, 2 plus 1, and 3 x's, 2 plus 1. And that was our goal, right? We wanted to make them into perfect powers so that they could pop out of the radicals, because 3 3s pop out of the radical as a single 3. 3 x's pop out of the radical as a single x. So that leaves me with an answer, cube root 12x. And like we said, 3 3s pop out as a single 3. 3 x's pop out as a single x, because you're just dividing the exponents. 3 divided by 3, 3 to the first. 3 divided by 3, x to the first. 12 is 3 times 4, which is 2, 2, 3. No triples there. So that can't be simplified. The radical's gone from the denominator, so everything is good. So that is a really great one to study for the test. Okay, for D, we have, let me get a different color. I'm bored with that color. So 5 fifth root of 2 into the 7th. So I see an exponent that's larger than the index, so that tells me to factor this. So there's only 1 2, so nothing we can do with that, but we can break this down into 7's not divisible by 5. 6 isn't divisible by 5, but we could make it into the 5th and into the 2nd. So now I have that perfect power of 5, so I can simplify that. And in the denominator, we have the 5th root of m, which nothing can be done with that. That's just m to the 1st. So simplifying, these 5 n's, will come out as a single n. 5 divided by 5 is n to the 1st. So outside we'll have n to the 1st, or just n. And then under the radical, we'll have the fifth root of 2n squared. It's not enough to come out of jail for either one of those. All over the fifth root of m to the first. So this is really the actual beginning of the problem. So it's simplified, except we can't leave that radical in the denominator. So I have to make 5 m's in order for them to come out, and I only have 1. So how many am I missing? I'm missing 4 m's. Because see here how we'll now have 5 m's? And that's my goal, because I need it to pop out as a single m. But whatever I do in the denominator, I have to do the same thing in the numerator. So fifth root of m to the fourth. So what that equals is n is still on the outside. And underneath the radical, we'll have fifth root of 2, and put your letters in alphabetical order, m to the fourth, n to the second. Notice all the exponents. 2 is to the first power, m's to the 4, n's to the second. They're all under 5, so we know that can't be simplified. And in the denominator, we now have fifth root of m to the fifth. Ding, ding, ding. That's exactly what we want. Because now on the next step, 5 divided by 5, the m pops out of the radical. And do you all remember what that's called again? When we take the radical out of the denominator? Rationalizing the denominator. So this is the process for rationalizing the denominator. 5 divided by 5, 5 m's come out as a single m, so now we have no radical in the denominator, and that's our goal. The numerator is just going to stay the same. In fifth root, I have to make this a little longer, 2 m to the fourth n squared. So that would be my answer. And the things you want to check before you box it, is there any canceling here, anything common? No. Any powers here larger than 5? No. Any radicals in the denominator? No. So that's how we knew to box it. We're good to go. So now would be a good time to turn off the video. You, not me. You turn off the video and work these two on your own and see how you do. And then turn it back on and you can check it with my video. So we have for E, 7, nothing to do up there. And we have a fourth root. And this is the one that we need to make perfect powers of 4. So we always want to factor everything possible. So 4 is 2 2's. And then we have an x cubed. And then we say to ourselves, what do we need to multiply by in order to make this 2 to the fourth and x to the fourth? That's our goal. We need 4 2's and 4 x's for them to pop out. So we say, what are we missing? Just like we did on the last page. We're missing 2 2's because we have 2 and we need 4. We're missing 1 x. Because we have 3, we need 4, but whatever we do down there, remember we have to do the same thing up here. And you can just write it as 4 on the next step. But for right now, I'll just write it the same way. Okay, let's see what we have now then. So in the numerator, we're going to have 7 times the fourth root of 4x. And there's only 2 2's and 1 x, so we know that can't be simplified. In the denominator, we're going to have the fourth root of 4 2's and 4 x's. So 2 to the fourth, x to the fourth. So 4 2's and 4 x's, 2 to the 4th, x to the 4th. So my final answer is going to be 7. And we already discussed the numerator can't be simplified because there's no groups of 4. But the denominator can, group of 4, group of 4. So 4 divided by 4 is 2 to the 1st on the outside. 4 divided by 4 is x to the 1st on the outside. Look for simplifying. No. Any radicals in the denominator? No. We are good. So that's a good one. A little too easy for the test, but it's good. This one's better, but either one of those you could study and you would be fine on the test. Okay, let's do this last one. So in the numerator, we have 3x. Nothing can be done there. In the denominator, we have 2 times the cube root of 5. So that means there's 1 5 there, right? And in order, and there's no simplifying to do in the whole problem, so we can start right now. In order for this 5 to come out, which is our goal, remember, rationalize the denominator means get rid of all the radicals in the denominator. We need to turn it into 3 5's. So we have 1 5. That means we need 2 more. Now we have 3 5's, which will pop out as a single 5 on the next step. But whatever you do to the denominator, do the same thing to the numerator. So now let's write what we have. 3x. It's not enough to come out. There's only 2, so we'll just write it as cube root 25. And I know that seems weird to leave a 25 under a radical, but this is a cube root, so I can't take the cube root of 25. In the denominator, we have 2 times the cube root of 5 cubed, which we know 3 divided by 3 brings 1 5 out. So our final answer is going to be, well, not final. I guess we got 2 more steps. 3x cube root 25 over 2 times, remember there's an imaginary times sign there. 3 divided by 3 is 5 to the 1st comes out. So now we can write our final answer. 3x cube root 25. There's only pairs in here, no cubes, so we can't touch that. And then our new denominator will be 10. And that's it. Okay, so that's called rationalizing the denominator when there's just one term. So no addition or subtraction in the denominator. All of these just have one term. If you look all the way up and down this page, let me lower it. You can see there was one term, just 20 in the denominator, one term, 25x squared or x cubed, one term in this denominator. So every single denominator in this only had one term, because remember, terms are separated by addition and subtraction signs. So on the next page, we're going to learn what to do when there's 2 terms in the denominator and we need to get rid of one or both of the radicals. So this is where conjugates come in. Remember how I said when we were doing multiplication, this is going to be an important part of our upcoming lesson? Well, this is that upcoming lesson. So now we're going to be rationalizing the denominator, which remember means getting rid of the denominator with radicals. So we can have fractions, we just can't have radicals in the denominator. And we're going to learn how to do it when there are 2 terms there. So you can see on all of these, 2 terms, 2 terms, 2 terms, 2 terms, 2 terms. So they're very different than the ones we just did because they have the 2 terms instead of 1. So what we're going to use, like I said, are conjugates, because if you look back at your multiplication section,